Hello, hello, hello. Welcome back to Data Science at Home, the podcast where we break down the latest and greatest in artificial intelligence, machine learning, and all things data science. I'm Francesco, and today I'm gonna be a bit, it's gonna be a bit longer today because I do have something super exciting. Uh, it's a very new paper that came from the same folks. You know already who they are. Deep sick folks. Well, sometimes we are waiting too long for ChatGPT to spit out a response. If you're using one of those, local models like OLAMA, Llama CPP, and many, many others now, thank God they're there. But they are slow, you know, and you see things loading word by word by word, and you're thinking, come on, man, I could write faster than this, right? Especially if you don't have a machine like these beefy beasts that can solve your problems for like 5 grand. Well, what if I told you that a team of researchers just figured out how to make language models work fundamentally differently and potentially way faster than they do today? So, today we are diving into a paper that is called Continuous Autoregressive Language Models, or CALM for short. You probably have heard of this. It's been on the news for a long time now. Well, not a long time. It just came out, but it has been, pretty viral. And now, despite the ironic name, this research is anything but calm. It's actually pretty cool and revolutionary. With respect to the way language models work these days, and has been working for the last 4 or 5 years, a bit less maybe. But okay, let's start with the story. Imagine you're reading a book, okay, and instead of reading word by word, you could somehow absorb entire phrases at once, right? So instead of reading the cat sat on the mat, that's one of these classic examples that we have in large language models, but also natural language processing back in the days. Now, instead of doing this word by word, imagine your brain goes boom and gets the cat sat on the mat, which stands for the cat sat on the mat as a unique token, right? Now that thing is called vector, and that's essentially what these researchers from Tencent WeChat AI team are trying to do with language models, which is super cool. Now, of course, there will be a lot of details that I'm gonna give you. That is all written in the paper. The paper is amazing. It's a very nice read. It's almost entirely self-contained. Um, you don't really need to look around, to see some other concept, unless, of course, you're a bit rusty on statistics. But that's fine. I mean, you can. There's Wikipedia for that. There's Wikipedia, not Grokipedia. That sucks. But that's a different story. All right, so before we go further, let me explain the problem we're trying to solve here, okay? So current language models, think GPT, think Anthropic, whatever, even the local models that you have, okay? Your Llama, all of them, they work like this. They predict one token at a time, okay? A token is basically a chunk of a word or a word, sometimes the whole word, sometimes just the root, sometimes a symbol, or a piece of the word, whatever. So each token carries something like between 15 and 18 bits of information, okay? So we are using these massive models with billions of parameters to predict these tiny, low information units one at a time, all right? That's what they do. And that's why they need an impressive amount of computational resources, because the way they solve this problem of predicting the next token given the previous 100,000 tokens, whatever, it's done token by token. Now, the researchers of this paper put it down very, very nicely. And I'm paraphrasing here. We've got this profound mismatch. Model capacity has scaled to unprecedented levels, but the task itself hasn't evolved. we are deploying models of immense power to predict simple, low information tokens one by one. It's computationally expensive, it's slow, and honestly, it's kind of inefficient. Bingo. So here's where Calm comes in. What's the big idea? Well, instead of predicting one token at a time, what if we predicted entire vectors that represent multiple tokens at once? Now, I know what you're thinking. Vectors, it's complicated. Stick with me because this is where it gets really, really clever. Now, the team building Calm, they also built something that's called an autoencoder. Okay, if you are on this show, if you have, if you are a follower of this show, we have talked about autoencoders a long time ago when it actually came out. What is an autoencoder? It's a model that can be trained to represent the same input in a more compressed form, right? So you autoencode, and then of course you can decode. So that latent space, that latent representation or hidden representation of the input, which is usually smaller than the input, can be decoded to reconstruct the input again, right? So that's exactly what they do. That's what it's an autoencoder. So they built this autoencoder, which is basically the equivalent of a compression algorithm, but for language. So you feed it 4 tokens, and it squashes them into a single continuous vector. And then when you need those tokens back, the decoder unpacks the vector that was generated by the encoder, and then you get the 4 tokens back, right? And then you can say, but yeah, I will never get the same thing back. Yes, almost. You get 99.9% accuracy back, right? So that's super strong. So 99.9%, it's insane, in fact, because it's like, I don't know how can I explain this to my sister. Putting 4 puzzle pieces in a box, shaking it up, and getting exactly the same 4 pieces back, perfectly preserved. Right? That's what 99.9 means. Now, here's where the magic really happens. And when I say magic, I really don't mean it because this is science. Instead of your language model predicting the next token, it predicts the next vector, and each vector represents k tokens each. Okay? In their experiments, they use k equal 4. In the paper, they use k equal 4, but more on that later. So instead of taking t steps to generate t tokens, now you only need t divided by 4 steps, right? So we've just cut your generation time by a factor of 4, which is not bad. Now, of course, this is not all gold. There are many consequences of this, and I will explain that more later. Because there are many catches, okay? The paper is nice, but it's also full of challenges. They are all solved, by the way. So there are several catches here. Now, the first problem, what is it? Well, when you are predicting continuous vectors instead of discrete tokens, okay, you cannot use the normal softmax function that current large language models use or rely on, right? You cannot do that. You know, that thing that gives you the probabilities for each possible next word. So the softmax is a function that you put an input, and that input is splashed over an interval from 0 to 1, where you have 0 to 100%. That's can be interpreted as a probability. Okay, that's what the softmax does for you. But of course, that doesn't work anymore. Because there are infinitely many possible vectors. Okay. Remember, now we are in front of continuous vectors, not anymore tokens. So how do you train a model when you cannot compute explicit probabilities? And the answer is, well, you go likelihood free. I love this term a lot, likelihood free. It sounds like something you would say at a statistics support group. I speak for a friend. Hi, I'm calm. I'm likelihood free. That's bullshit. Anyway, likelihood free is a term that comes from the statistics world, and they use something called the energy score, which is a fancy mathematical tool that lets you train the model by comparing samples instead of computing probabilities. If there is one thing we learned from statistics back in university and academia, is that when you cannot have a probability distribution, you start counting samples, right? These are usually called model-free statistics, because you don't have a model. Model-free in the sense that there's no model. So imagine a Gaussian for which you don't have the Gaussian formula, so you don't know the mean, you don't know the standard deviation, you don't know these things. You just have a bunch of samples and you just measure, you observe the samples, right? That's kind of the trick. So it's based on something that is called strictly proper scoring rule, which is something that, again, you can search from Wikipedia. I did that. I didn't know it existed. But basically means that the model is incentivized to learn the true distribution of the data. Okay? Now, the second problem that they solve is how do you evaluate a model that doesn't give you probabilities? Remember, we are in front of continuous vectors again. So normally we use something called perplexity. You probably have heard this name already a number of times. They even built a company there that is not sponsoring this episode, so mark them, which measure what's perplexity? It measures how surprised the model is by the actual text, right? But perplexity needs probabilities. So the researchers invented a new metric, which is called the Breer LM. Now, they didn't invent anything, in fact. Breer score has been around since, guess what, the 50s, 1950. And it was originally for weather forecasting. So I went on Wikipedia, again, not Grokipedia. You have to use Wikipedia. That's the real thing, the thing written by people. The Breer score is a strictly, is a strictly proper scoring rule that measures the accuracy of probabilistic predictions. Now, listen to this. For unidimensional predictions, it is strictly equivalent to the mean squared error as applied to predicted probabilities. I mean, this is something, so simple. It was proposed by Glenn Wilson Breer in 1950. And if you look at the most common formulation of the Breer score, it's basically 1 divided by n, where n is the number of forecasting instances, multiplied to the sum over t from 1 to n of what? Of ft minus ot. Ft is the probability that was forecast, and ot is the actual outcome of the event at instance t. So basically, the predicted value minus the real value, right? The ground truth. What is that? It's a distance or an error, right? So that error elevated to the power of 2, sum, and then divided by n gives you what? The mean squared error, all right? So in fact, the Breer score for unidimensional predictions is exactly the mean squared error. To make you understand that these are not this is not rocket science. This is like kind of 101 statistics or statistics 101, right? It's very simple. That's why this paper is great, because it's like it puts together relatively simple concepts and makes something that is astonishing. Okay, now this Breer score, all right, initially it was used for weather forecasting. These researchers figured out how to estimate this Breer score using only samples from the model. So no probabilities needed. And get this, they tested it against traditional models and found that this score, this Breer score, correlates almost perfectly with the standard cross-entropy loss, which is what, currently is used by neural networks and large language models. We're talking about negative 0.966 Pearson correlation, which is incredibly high. That's like finding out that you can measure, let's say, temperature with a completely different tool, which is not a thermometer, and getting exactly the same readings as a thermometer, because they are so highly correlated that this new tool, let's say a rock that you find, it correlates so well to the actual thermometer that it works. Okay? Now, the third problem, and this is one of my favorite, is called temperature sampling. Now, when in ChatGPT, they try to sell you a model that is more creative by increasing the temperature, okay? Or less creative, which means more focused. Now, there's nothing related to creativity in human terms or being more focused as a human. That's not that. There is a parameter that gives you that kind of feeling, or well, tunes the model to behave in different ways, being more quote unquote creative or quote unquote more focused. It's because you're randomizing more or less. So it's a parameter that you use to tune randomness essentially. Now, that works by manipulating the probability distribution, okay? But again, Colm doesn't have explicit probabilities, so they developed this beautiful rejection sampling algorithm. I remember this stuff from school, to be honest, statistics at school, at university. So the basic idea, if you want to simulate a distribution raised to some power, you can do so by repeatedly sampling and only accepting when you get the same result multiple times in a row. That's why it's called rejection sampling algorithm. Okay. Now, for example, if you want probabilities squared, you sample twice and you only accept if both samples match, right? So the probability of that happening, what is it? It's exactly the square of the original probability. This is mathematically elegant and it works. Okay. It works since centuries. Now, does this actually work, this all Colm thing? Does it perform well? Because that's what we care of, right? We are so superficial these days that we skip all the mathematics and the science. It's okay, all nice, beautiful, whatever, but does it work? The short answer is yes, it does, with some caveats, but it works. So the Colm model with k equal 4, okay, meaning that there is 4 tokens per vector, it achieved comparable performance to strong discrete baselines using something like 44 fewer training floating point operations and 34% fewer inference floating point operations. That's massive. 44% less floating point operations, called flops, and 34% in inference, 34% less flops in inference. It's incredible. So if you want to put this in perspective, imagine that if your phone battery suddenly lasted 50% longer because someone figured out a smarter way to process information. That's how good this is, okay? Now, where is the catch? The catch is that when you use k equal 1, that is, the vectors are representing just one token, so it means that, it works, it's doing the same thing as a regular GPT model or a traditional GPT model, but with continuous vectors. It actually performs worse. And that makes sense because the model has to work harder to deal with the continuous prediction task. So remember, it has to, from that token, it has to map that token into a continuous vector for no reason at that point because it's just one. Then decode that to feed it back. It's like, it's more operations. It's slower and it's worse. Now, where's the part that excites me? As you increase k, you get better and better efficiency. So k equal 2 nearly halves the cost with the minimal performance drop. When k is equal to 4, it surpasses the baseline. It's a kind of a new knob that you can turn, a new axis for optimization. How many tokens can you pack into a vector now, right? Now, let's talk about this autoencoder, just a tiny digress, because the engineering here it's pretty clever, and I want to mention this. Now, of course, they didn't train a basic autoencoder, okay? These are people from Tencent. These are pros. So they made this autoencoder variational, okay? Well, you know what it means? It means that it maps to a probability distribution, not a single point. So they added dropouts to make it more robust to noise, as we usually do. They used something called the KL clipping. KL stands for Kullback-Leibler divergence. Blah, I could never spell that. Anyway, KL clipping to prevent something that is called posterior collapse, which is when some dimensions of your latent space basically give up and the whole thing becomes useless, right? I don't want to enter too much in detail about this because there is a paragraph, a couple of paragraphs in a section on the original paper at page 3. It's called Robust Vector Representation 3 and 4, where they actually mention this and they explain how they prevent posterior collapse with formulas and representations, and it's like it's a relatively easy read if you know a bit of statistics. Okay, so I will definitely recommend reading the paper because it's very well written and a very good learning experience. Absolutely. Now, a latent space that can handle being perturbed by a Gaussian noise with a standard deviation of 0.3, that's the example they made. It's a shitload of noise, okay? And they can still reconstruct the original input with 99.9% accuracy, okay? It's incredible. I don't know how to explain this. Like 30% noise, standard deviation, sorry, 0.3, it's huge. It's really huge. It's a lot of noise. So to put how can I say, to push the entire autoencoder to kind of the limit, and it still performs well. Now let me share some of my favorite details from the paper because there are some real gems in the paper, as I said. Highly recommended read. I will provide the links and the paper itself in the show notes of this episode on the official website, datascienceathome.com. But of course, feel free to jump on Discord. Let's get on a chat or share your thoughts or your findings if you have any. That's an amazing stuff. So the first thing they did was, they tried using diffusion models and flow matching for the generative head. These are popular techniques for generating continuous data, and they are very slow. Okay, so they need dozens or hundreds of iterations to generate a single vector, which of course defeats the whole purpose of making things faster. So they used something called energy transformer instead of the diffusion model. So energy transformer can generate high quality vectors in a single step, right? And that saves you a lot of time. The second problem is that they found something really interesting about the model's input. So initially they thought, hey, we are predicting vectors, so let's feed vectors back into the model as input. Wrong. Didn't work. So the continuous vectors apparently are too compact and compressed, and the model struggles to unpack the semantic information. So instead, they decode back the vector back to discrete tokens, and they feed those into the model again. So it's like the model needs to see the actual words to understand what's going on, and not just the compressed representation of the words. Okay, so that's a very interesting finding. It would be very natural to feed back because you say, this is a compressed version, 99.9% accuracy reconstruction. Bingo, I'm gonna feed the network again with the compressed version of the input. No, don't do that. Didn't work, right? So in case someone is doing that, don't do that. Read the paper. The third challenge, and this is really cool, the training curves look totally different from normal language models. So you have to know that traditional transformers learn quickly at first and then they plateau. So they are learning a relatively simple task, which is indeed predicting the next token. So they make fast progress early on. What about Calm? Calm has this slow, patient learning curve that eventually gets steeper. So it starts off slower, but then it takes off. Probably that's why it's called Calm. I don't know. Probably not. Anyway, the researchers explain this beautifully, in my opinion. And they say that while baseline models are learning to predict simple, low information discrete tokens, Calm has to learn to model complex, high dimensional distribution of continuous vectors, which is a harder task. Okay? But once the model figures that out, it can leverage its larger capacity for sustained improvements, which makes a lot of sense if you think. It's like, learning to juggle versus learning to solve Rubik's Cubes, right? Juggling is something that you can pick relatively quickly. Solving Rubik's Cubes takes longer to learn, but once you get it, you can solve increasingly complex puzzles over and over. And so, it's tough at the beginning, but then, once you break that barrier, it's kind of all downhill, right? That's how Calm works. The learning curve of Calm works. Now, I want to be balanced here. This is very early stage research. So the authors themselves point out several limitations and areas for future work. So for one thing, there is the autoencoder. It's context free, okay, which means that it processes each chunk of tokens independently. Now, to be fair, they already mentioned that a context-aware autoencoder also looks at previous chunks, could be more powerful, and that's the most, natural evolution in a next paper or a follow-up for sure of this amazing research. The generative head, the part that predicts the vectors, could potentially be integrated more deeply into the transformer architecture instead of being separate module again. And another thing which is very crucial, they haven't tested this at really large scale yet. So all the experiments that are mentioned in the paper were done with models up to 1.8 billion parameters. So the question is, what happens at 70 billion or 400 billion? We don't know. That's the problem. So there's also this intriguing hypothesis they mention. Maybe larger models can support higher values of k, which would be great, because instead of compressing 4 tokens into a vector, why not 8 or 16 or 32? You get the point, into a single vector. So that would mean even bigger speed ups, probably. Who knows? So something that we should be trying. Well, they should be trying. So let's zoom out for a second and think about what this means for the field, because we've always been kind of okay, research is good, but what are the practical implications of this, right? So for the last few years, we have been scaling, and for decades in general, the way we have been doing deep learning especially, and scaling not only language models, but models in general, deep learning based models. We have been scaling these monsters along 2 axes usually, which is more parameters and more data, right? Bigger and bigger models trained on more and more text data in general. And it's worked, kind of. So we've gone, when it comes to large language models, from GPT-2, GPT-3, GPT-4, 5, 6, and God knows how many other in the series. So unless probably they finish the money, hopefully soon. Now, more or less, each of these models had more capacity and was more capable. Now, more capacity, obviously, because there is more space for parameters, there's more space for data. More capable, not so sure, but okay, that's what they claimed. Now, what Calm does, well, they introduce a third axis here, which is called semantic bandwidth. Because, this K that you use to compress tokens, a certain number of tokens into a continuous vector, well, that represents the semantic bandwidth. So how much information can you pack into each step of generation? How much information can each step of generation carry? Okay, which is no longer one single token, 15, 18 bits, but it can be a lot bigger than that. So it's like we've been trying to make our internet faster by building more servers, laying more cables, and then all of a sudden someone comes and says, hey, what if we could also compress the data better? And now all of a sudden the same infrastructure, the same cable can carry a lot more data because it's compressed. And guess what? The compression algorithm is almost free. That's how powerful this thing is. So this is what excites me. This could make language models a lot more accessible than they already are. If you can get similar performance with significantly less computation, that means smaller companies, researchers at universities, even hobbyists like you and I, they can train and run much more powerful models at home. This truly democratizes the technology. And don't forget that the big players who are building these massive models, they have this huge barrier that prevents, in fact, everyone from fine-tuning and retraining these beasts, because it's not feasible. I mean, nobody has $25 million to retrain a model from scratch. Nobody has infinite energy or infinite infrastructure, right? So that, barrier that in fact is centralizing language models and artificial intelligence in the hands of a few, it's just given by the technological requirements that these models need. in terms of energy, time, and of course, US dollars. So yeah, that is of course the environmental implications. We are in Europe, so we have to say that. Uh, that was sneaking into the door. Training large language models uses enormous amount of energy. If you didn't notice, we are talking about the carbon footprint of multiple transatlantic flights for a single training run. Right. So if we can cut by, let's say, 44%, let's keep these numbers. 44% of that means that you can run the training twice instead of once, right? Or if you have to train it 100 times, it's like training it 50 times. It's something like that. It's like huge. It's not just good for your pockets, for the wallet, but it's good for the planet in general. Now, I want to talk about something that might not seem important, but actually is. The naming and presentation of this research. They called it CALM, Continuous Autoregressive Language Models. It's a nice acronym. I love it. CALM, peaceful. It's ironic given how revolutionary the idea is. But more than that, which is semantics and fun stuff, they structured the paper around solving quite big challenges and very specific challenges. For example, how do you train without likelihoods? How do you evaluate without likelihoods? How do you do temperature sampling without likelihoods? Each of these massive problems gets its own solution, complete with theoretical proofs, empirical validation. It's like watching someone carefully dismantle a lock one pin at a time, and you have all it there in front of you. So this is very good research. This is how, in fact, good research should be done. Identify the core challenges, solve them systematically, validate that your solutions actually work. There's no hand waving. There's no we'll leave that for future work or to the reader as an exercise on all the critical components. No, it's all there, all self-contained. You read the paper from beginning to end and you know what's going on. Now, let me give you a few more technical nuggets for the nerds in the audience. I know you guys are there, and I love you because I'm one of you. The energy loss they use is based on something called a strictly proper scoring rule. Now, what makes it strictly proper? Again, you go on Wikipedia, not Grokipedia, and if you click on the Breer score, the definition, it says the Breer score is a strictly proper scoring rule. You go to the definition of that, and there is a scoring rule S is proper relative to F. I'm reading. If, assuming negative orientation, its expected score is minimized when the forecasted distribution matches the distribution of the observation, which is very clear, isn't it? No, it's not. So I give you the long story short. What makes it strictly proper? Well, it's uniquely optimized, this rule. It's optimized when your predictive distribution matches the true data distribution. So you can't game it by reporting a biased distribution. It's like a test that can only be aced by telling the truth. Okay? So the Breer LM metric they invented, which they didn't invent, in fact, they reused. They compute it using n-grams from 1 to 4, then take the geometric mean. So they're not just looking at individual tokens, but they're evaluating how well the model generates coherent sequences, which is very clever. And last thing, the approximate temperature sampling algorithm for low temperatures, that's asymptotically unbiased. Again, statistics 101, and you understand the meaning. As you increase the batch size, it converges to the exact distribution you want. It's an approximation that gets better and better the more resources you throw at it. And eventually, asymptotically approximates that. Isn't that cool? Statistics. You see? Academia is useful sometimes. Anyway. All right, let's play the game that I love the most. What could go wrong? Welcome to What Could Go Wrong. Now, whenever we have these new, exciting new technologies, it's worth thinking about the challenges. There are several, as we said. Challenge one is, the approach is fundamentally more complex than standard language models, obviously. There is an autoencoder in the mix that you need to train. There is a special generative head, likelihood-free training. There are more moving parts, clearly. More things that could break, more hyperparameters to tune. For big companies, this, with lots of resources, this doesn't mean anything. Like, it's fine. For someone trying to train their first language model, might be overwhelming. The second challenge is about the autoencoder. The autoencoder is the bottleneck of the entire system. Everything depends on the autoencoder because the autoencoder will map tokens to vectors and back with high fidelity, 99.9 accuracy. If that breaks, the whole system breaks. It's like building a house on a foundation. If the foundation cracks, you are in trouble, okay? The third challenge is that we don't know how this scales yet. Maybe at 100 billion parameters, the benefits disappear. Maybe they get even better. We don't know. We need more research to find out. And I'm pretty sure we will read soon about these new findings. Now, it's okay, to be honest. These are all solvable problems, in my opinion. These are engineering challenges. They're not fundamentally impossibilities, right? And that makes the whole thing exciting because that means there's room for improvement. There's room for innovation. So let me tell you about my favorite implication of this research. And it's something that the authors mention almost in passing. They point out that the Breer-LM metric and the likelihood-free evaluation framework could be useful for other implicit generative models too. Okay, diffusion models for text, for instance, have always been tricky to evaluate because computing their likelihood is hard. So not only have they potentially made language models more efficient, but they've also given us new tools for evaluating a whole class of models, and that's awesome because these are free tools now. The temperature sampling algorithm, that's a general tool for any implicit model over discrete spaces, if you think. It's like, you're building a house and accidentally invent a new type of hammer that allows you to build better cars. That's how useful these things are, Science, bitches! All right, prediction time. Where do I think this research goes from here? Well, first, I think that we will see iterations on the autoencoder. In fact, I don't think this. It's been written in the paper. I'm not stealing credit to anyone. So maybe someone figures out how to make it context aware. Maybe the same folks will figure that out if they didn't already. The problem there that I see is, can you do that without adding too much overhead? Probably that's the challenge. But okay, more on that another time. Maybe someone finds a better way to learn semantically structured Latin spaces where similar meanings are close together in a vector space. We have seen that, semantic space and embeddings. Probably that could work here as well. Who knows? Throwing ideas. The second thing, I think that we will see experiments at much larger scales. This model is so appealing that, if I were a big company, I would use a bunch of millions to try it out on a 70 billion parameter call model, whatever. So I would do that exercise because the benefit could be incredibly profitable. Like if you can prove that a 70 billion parameter model performs as good as a 400 billion parameter model with a calm alternative, well, you will save a lot of money later, my friend, for sure. The third is, and this is kind of a wild card for me, maybe someone figures out how to do this with even higher compression rates or ratios. What if you could compress, for example, 16 tokens into one vector, or 32 or 64 or whatever? Okay, at some point, you're no longer predicting, well, tokens for sure not, but not even paragraphs. You might be predicting ideas, okay? Because your new currency becomes, instead of the token, the new currency is the vector. And if that vector represents a certain or relatively high number of tokens, well, that vector is no longer, it's comparable to an idea, to a concept, not just a bunch of words, right? And then I think we'll see hybrid approaches. Maybe you can use Calm for the bulk of generation where you want speed, and switch to traditional token by token generation for the final polish or for the tricky parts. Best of both worlds in engineering usually pays well. Who knows? This is like super novel, and many opportunities there. Now let me bring this home with a broader thought. And again, I want to be super critical here. We are in this interesting moment in AI research where we are starting to question fundamental assumptions. And for years, everyone just accepted that language models work by predicting one token at a time. And then, someone asks, but why? In my opinion, that's the question that leads to breakthrough. Not how can we make this 5% better, but why are we doing it this way in the first place? And Calm, in my opinion, is part of a larger trend of rethinking the foundations of language modeling. We have seen many things in the years. We have seen mixture of experts. We have seen state space models. We have seen various forms of efficient attention, for example, attention mechanism. Each one is challenging a different assumption, exploring a different part of the design space. And I think that's healthy. We should be constantly questioning, constantly experimenting. The first way we figure out how to do something is rarely the best way. So here's my hot take. 5 years from now, when we look back at language models in 2025, we're going to think, wow, we were doing it the hard way. Just like how now we look back at early neural networks without residual connections or without attention mechanisms, and we think, how the heck did they even train those things, right? So Calm, for sure, might not be the final answer. For sure not. But in my opinion, they're asking the right questions. And sometimes asking the right questions is more important than having the perfect answer. Now, I know that, I want to take a moment again to talk about something that's been bothering me for a while, and hopefully you too. Especially, I'm referring to the research community out there. But of course, also to the many practitioners and also startup founders who are relying on these big names, OpenAI in premise, to build their products. So here we are getting excited about real open research from teams like Tencent's WeChat AI team, complete with mathematical proofs. There is openly shared code. There is a code repo that you can test at your place. Reproducible experiments, all that stuff is at your disposal, okay? This is what research should look like, guys. Meanwhile, OpenAI, and I'm calling them out, has essentially become a black box that occasionally drops glossy product announcements and marketing materials. Remember when they used to publish actual research papers, when open actually meant something in their name. Now we get blog posts that read like product brochures. GPT-4 is amazing, trust us. Here are some cherry-picked examples. And by the way, when you go on x.com, you find a bunch of OpenAI influencers parroting the same words that their daddy Altman has told them to. But where's the science? Where are the architectural details? Where are the training procedures that let the community learn and build upon their work? Now, of course, they are a company. They have a competitive reason for secrecy. But, let's not pretend they're still a research organization contributing to the scientific community. They are not. They've become just another tech company guarding their trade secrets, and we should stop giving them credit for being researchers. The real innovation, it's happening in places like this. Teams publishing full papers, sharing code on GitHub, contributing to the collective knowledge of humanity. That's how science advances, not through proprietary models hidden behind APIs where we can't even see what's under the hood, and when, by the way, all the data that have been used for training is ours, is public data, and even private data. You just can't claim that because in many countries that's illegal, okay? So Here's my plea to the AI community. Let's celebrate and support the researchers and the organizations that actually practice open science. Let's hold companies accountable when they claim to be doing research but will not show their work. And maybe let's stop treating OpenAI like they are still the scrappy research lab they pretended to be 5 years ago. They're not open. They're not really contributing to scientific discourse anymore. And honestly, papers like Calm show us what we're missing when research stays locked behind closed doors. We deserve better. Science deserves better. Okay, rant over. But seriously, open science matters, folks. Support researchers who share their work. I'm off.